All right, good morning, everybody. So today we're going to get into chapter 13, and we're going to talk a little bit about allylic radicals and allylic cations today, and really start reviewing resonance a little bit, because resonance is going to be a vital part of this chapter. And we're also in this chapter going to talk about a very important reaction called the Diels-Alder reaction. We're just not going to talk about it today. But it is a very important reaction that resulted in a Nobel Prize. Before we get started on this, though, let's quickly review the stuff that we talked about last time. And we were talking about organometallic reagents reacting with carbonyl compounds. What organometallic reagents did we talk about specifically? LAH is not an organometallic. Remember, that's a hydride. Right, we talked about Grignard reagents, so the MgBr, alkyl or aryl, magnesium halides, right? So the halogen can be chlorine, bromine, or iodine. What else did we talk about? We talked about the alkyl lithiums, and they behave very similarly in all aspects except what? They're both really good nucleophiles, right? But the way they attack in terms of arrow pushing is the same. There are some slight differences, but that's a true statement, but not what I'm after.
Really basic.
Yeah, the alkyl lithiums are really strong bases. They're among the strongest bases that we know. They're pyrophoric, meaning what? What is a pyrophoric compound? It is combustible. So when we take a concentrated alkyl lithium and we place it in the open air, it will spontaneously burst into flames. Makes it kind of a challenge to deal with, right? Grignard reagents are not that way. So on a practical standpoint, even though they behave similarly, there are some real differences. And then we talked about a third organometallic reagent, the alkanides, right? So some type of carbon-carbon triple bond with an associated metal. And here we have a situation where we actually have an ionic bond. These are more covalent. But nonetheless, they all behave as carbanions, C-. And so if we take let's just use Grignards as our example, because that's kind of my go-to. If I take a ketone and I react it with I'm just going to put G for Grignard, what do I get? What's the product? What kind of alcohol? A tertiary alcohol. And I'll just put G there. And that's after workup, of course, right? If I take an aldehyde and I react it with a Grignard, what do I get? I get a secondary alcohol. If I... Crap, I got blue stuff on my shirt. If I take an ester and I react it with Grignard, what do I get? I get a tertiary alcohol again. Remember, we will actually add two equivalents of the Grignard. We will make the tertiary alcohol, and of course we have that ends up being a leaving group. If I take formaldehyde and I react it with a Grignard, what do I get? I get a primary alcohol. Right? If I take a Grignard and I react it with carbon dioxide, what do I get? I get a carboxylic acid. So as you're seeing, the power of the Grignard, right, is that I can make a lot of carbon-carbon bonds. Look at where the G's are bound. They're all bound to carbon, right? And I can convert carbonyl-containing compounds, including carbon dioxide, into new compounds. So I can make everything from primary alcohols to tertiary alcohols. I can make carboxylic acids. This type of stuff needs to be rolling off your head pretty easily. You need to know the functional group transformation, right? Now, you can struggle through and figure out the mechanism and figure out what these things are doing, and that's one layer of the onion that you need to know, but that's a higher level. But at the very fundamental level, when you see a problem, you need to know, I've got a Grignard, I've got a carbonyl, I know what I'm going to get, right? You worry about the mechanism second. So you need to know what your functional group transformations are. Very, very important that you focus on that, okay? So those are the things that we can do with Grignards. And we know that the same thing's going to happen with the alkyl lithiums and the alkanides, more or less, okay? So, again, today we're going to jump into Chapter 13, and we're going to start talking about allylic radicals and allylic cations. I'm not going to go through all of the resonance rules. That's back from 255, but you need to read those and get refamiliarized with resonance. But today we're going to figure out what resonance really means in terms of orbitals. So in this chapter, we're going to talk about orbitals, and I know it's not your favorite topic, but it is very important because, again, the Diels-Alder reaction can't really be explained unless you have an understanding of orbitals. And so we're going to have a little better understanding of orbitals than what we currently have. At the moment, your understanding of orbitals are kind of atomic orbitals, right? You have a p orbital, an s orbital, sp3, an sp2, an sp. You've all got that down pretty well. But now we're going to be talking about how we make molecular orbitals from atomic orbitals, okay? Not just hybrids. So that's what we're going to talk about today. So when we look at conjugated systems, we actually have to think about resonance. So here we have a situation where we have an alkene. On one side we have a carbanion, on the other side we have a carbocation, right? We can show different resonance structures for this particular species. Which one of those three is the major contributor? The middle one. And why? No charge separation, right? Does that mean that the others do not contribute to the hybrid? No, it doesn't mean that at all, right? It just means that they're a very, very small contributor to the overall hybrid. And in fact, you would not draw these out as such, right? You would draw it on paper like this. Now, this is a conjugated system. How do I know it's a conjugated system? What? I have what? I have resonance. What does that mean? So electrons can be delocalized over multiple atoms. They don't belong to any particular atom. And which electrons are those? The pi electrons. The pi electrons, right, can actually be delocalized. And so when we're drawing the resonance structures, we can see that the N carbons can actually have partial positive or partial negative character. And we can never put those positive or negative charges on these internal carbons because of our resonance rules, right? So this is an example of a conjugated system. So if you think about it, we've got a p orbital, a pi bond, a p orbital, and we can draw different resonance structures. Here we also have resonance, right? We can draw arrows that show the movement of this electron from this carbon to this carbon. However, what arrow would we have to use there? We would use a single barbed arrow, right? Where is the electron never at? It's never in the middle carbon, right? And by pushing arrows, there's no way to do that. But that really doesn't explain why there's never that single electron in the middle carbon. It actually has to do with how the orbitals are. And we're going to talk about that. The resonance rules and the arrow pushing actually has reality in orbitals. Okay? And so it's very, very important that we have an understanding of that. Now, the same thing for the cation and the same thing for the carbanion, right? We can move these electrons. However, the arrows that we would use to show the movement of these species would be what here? For the last two, what would we use? Single barb or double barb? We would use double because we're moving a pair of electrons. We're moving the pi bond. We're going to move the pi bond from here to here, and that leaves the positive charge there. We're going to move the anion, push those two electrons here to form the pi bond, and move those two electrons onto that carbon to make the anion on that carbon, right? And so these are said to be conjugated systems. What do we know about conjugated systems? Are they more stable or less stable? They are more stable. The more resonant structures that we can draw, the more stable the species, correct? Okay, and so that's going to have some important consequences to us when we start talking about some of these reactions with these conjugated systems. Now, if you think about this allylic radical, why do I call this an allylic radical? What does that mean? It is a free radical, but why is it allylic?
You have a sigma bond, the carbon connected to the sigma bond from the double bond.
Okay, so if anytime I have an alkene, the carbon that's directly attached to that, if it's not part of another double bond, that is called the allylic carbon, right? And so this is an allylic system. Now you can draw the allylic system this way, and we can use this arrow, which indicates what? Resonant structures. So what does that mean? Have we moved the atoms? No, we've just moved the electrons, right? Actually, we've moved an electron from over here to over there, right? But in reality, the way that this system looks, it looks like this. Okay, so we've got the 3 carbons, we've got our 3 p orbitals. There's a p orbital here, a p orbital here, and a p orbital there. So we've got those 3 p orbitals, and each p orbital actually has an electron, right? 2 of which just happen to be spin paired and creating a double bond, and 1 that is not paired up and creating the radical. And that's really what's going on in terms of the orbitals. But most people don't like to draw p orbitals on every carbon atom that they're dealing with. And so they will quite frequently draw this like this. What does that mean? Okay, so that indicates that over those 3 atoms, the electrons are delocalized, and it's a radical, right? So I know that I've got a pi bond and a radical when I look at this structure. And I know, since this is an allylic radical, that over these 3 atoms, the electron, the single electron, the free radical will either be on this one or this one, but it can't be in the middle. I know that intuitively. You all will know that intuitively as you work with it more. Okay? But that's another way in which we can indicate delocalization of electrons across multiple atoms without actually having to go in and draw the different resonance structures. Okay? Now, allylic systems have special chemistry. So, for example, here we have propene, right? So we've got a carbon-carbon double bond and a CH3. This is the allylic carbon. Everybody agree with that? And if we take this and treat it with bromine or chlorine at room temperature, that should be a V there, no light, we see the formation of a dihalide. It goes through the polonium ion. We end up getting the anti-addition of halogen across the carbon-carbon double bond. That's back from chapter 6 or 7, right? Nothing special. It just added halogen across the carbon-carbon double bond. It's just an addition reaction. However, it was discovered many, many years ago that if you run this same reaction at either high temperature or in the presence of some type of peroxide, you actually don't add the halogen across the carbon-carbon double bond. You do a substitution reaction and replace hydrogen with a halogen on the allylic carbon. What kind of mechanism do you think that is?
Substitution.
It is a substitution, and it is a free radical mechanism. How do I know it's free radical, other than the fact that I just told you? What favors free radical chemistry? High temperatures. And I said peroxides, right? So peroxides can be free radical initiators. Okay? It turns out that diethyl ether, if you let it sit in a room with oxygen for a while, over time, it will oxidize and generate some peroxides. And that's how this was discovered. Somebody actually went and wanted to do an addition reaction across the carbon-carbon double bond of something similar to this, and they used old ether that had a lot of peroxides in it. And when they did this reaction, they actually found that they didn't get any addition across the carbon-carbon double bond. They got allylic substitution. And so they were able to deduce that what in fact was happening was a free radical mechanism. Okay? And so as long as you keep the halogen concentration low and the temperature high, you can get this allylic substitution, and you can generate alkyl halides. Okay? And these alkyl halides are useful. We can use them to make Grignard reagents. We can use the halogen as a leaving group. We can use it to be attacked by nucleophiles. How else do we know of how to generate alkyl halides? What other reactions do we have in our toolbox to make an alkyl halide? Not that particular alkyl halide, just alkyl halides in general. How can we make alkyl halides? Addition of what? Okay, that would give us a dihalide. But we can do an addition across a double bond of what to give us just a typical halide? HX. So we can take an alkene and react it with HCl, HBr, or HI, and we can get an alkyl halide. Right? How else what other functional group can we convert into an alkyl halide? How? How can I take an alcohol and convert it into an alkyl halide? What reagents do I need? I can use H2SO4 and what else? Okay. So HBr will do this, right? I can use HX, I can use HBr, HCl, HI will convert alcohols into alkyl halides. What else will? I can use sulfuric acid and salt like sodium chloride or sodium bromide. That generates HX, which is where I thought you were going with that question. Right? What else? Two other reagents that we talked about. Actually, three reagents that we talked about. How about thionyl chloride, SOCl2? You guys are going to have to start getting these reagents memorized. We got to be able to have these roll off our head. Thionyl chloride plus an alcohol gives me what? What does it give me? What kind of alkyl halide? If I'm using thionyl chloride. Think of its name. SOCl2 is the reagent. Thionyl chloride plus an alcohol gives me what? What does it give me? What halogen is there to make a halide with? Chloride, right? So I know if I take an alcohol thionyl chloride, I'm going to get an alkyl chloride. That's what we're going to get, right? What other reagent do we have that can convert an alcohol into a different type of halide? Let's say we want to get an alkyl bromide. We can use HBr, but there was a reagent that we talked about, PBr3. Pabst Blue Ribbon the third, right? PBr3. There was one other reagent that we talked about. And it was coupled with hydrochloric acid to give alkyl chlorides. Pardon? Zinc, which we called Lucas reagent, right? Which is a mixture of zinc chloride and hydrochloric acid. There are a lot of ways of making alkyl halides right now and that you've been exposed to. We can also make alkyl halides by free radical halogenation of an alkane, right? We can use all these different ways now of doing this chemistry. And so if you think about allylic halogenation, it's just one more tool in the toolbox. And it allows us to specifically put a halogen on the allylic carbon. I can't do that with these unless it's an allylic alcohol, right? If it's just a carbon that's allylic with hydrogens on it, I'm going to have to do free radical halogenation. I can't use HCl or HBr or whatever. And so we know we've got the initiation. The chlorine decomposes into chlorine radicals. I know that's an initiation step. I then have the first propagation step where the chlorine radical abstracts a hydrogen. We end up with the allylic radical. The allylic radical then reacts with the chlorine gas, makes the alkyl chloride plus the chlorine radical. And what happens to this? What happens to this radical? It goes back, and this continues. And it continues on until we start to run out of reagents. And then we start having termination processes, right? And so this carries the chain and allows us to continue on. This reaction actually works quite well. You can do allylic halogenation very, very easily in a laboratory setting, okay? We know that radical stability typically follows carbocation stability, right? With one exception, and that is that we can actually have methyl radicals. Can we have methyl carbocations? No, not, well, technically yes you can, but it's so rare, right? It would win you a Nobel, actually it did win a guy a Nobel Prize. But it's not very practical. But we can practically generate methyl radicals, right? So we know that methyl radicals are less stable than primary radicals, are less stable than secondary radicals, are less stable than tertiary radicals, and tertiary radicals are less stable than allylic radicals. Why are allylic radicals, when these look like primary radicals, more stable than all these things? Resonance, right? And what is it about resonance that helps stabilize it? It's that delocalization of the electrons that has an energy-lowering effect on the stability of the system. And if you look at it, you can find the bond energies of all these things pretty straightforward. But really, you just need to memorize this trend, okay? So anytime we have a radical next to some type of carbon-carbon double bond, we know that that's going to be a lot more stable than these other things because of resonance, okay? Now, there are some practical things to be thinking about when we think about free radical allylic halogenation. You want to have a free radical initiator, in this case peroxide, or strong light like UV light, right? But you also want to keep the concentration of the halogen low. Why is that? That's right. If I have too much halogen around, it will react with the carbon-carbon double bond by addition, right? And but if we keep the concentration of the halogen really, really low, that reaction rate is going to be slow. How do I know that that reaction rate is going to be slow if the concentration of the halogen is low? Okay, it would be limiting, that's true. But why would that slow down the reaction? That might be true, I don't know. The rate of reaction of the addition of an alkene and a halogen is going to be dependent on the concentrations of what? The alkene and the halogen. Both of them have to come together in the rate determining step, which is the formation of the holonium ion. So if I keep the concentration of the halogen really, really low, let's say approximate 0, really close to 0, then that rate of reaction almost has to be 0, right? But the rate determining step in a free radical reaction is not the reaction with the halogen. It's the generation of the radical itself. That's the highest energy step. Okay? So that's why you can keep the concentration low, avoid one reaction, and allow the other reaction to occur. It's all about kinetics. Okay? Now, the way to keep bromine concentration really, really low is not to use bromine itself, Br2, but to use the reagent NBS. And we've talked about that before. NBS will react slowly to generate small quantities of bromine in solution. And it keeps the concentration relatively small. Where else did we use NBS last semester? Anybody remember? What reaction were we doing where we used NBS last semester? Say it. Bromo hydrins. Remember, NBS plus water is the same thing as bromine and water, and we generated bromohydrins, right? And I said that you can just use bromine and water, but NBS is really convenient because it's a nice white crystalline solid. You can weigh it out. You don't have to worry about all that bromine vapor and gas getting out. It's pretty convenient to use. You can weigh it on a scale real easy. But if you throw in peroxide, you can also do free radical halogenation at the allylic position. And this actually turns out to be quite practical. And this is typically what we do in my lab when we're trying to make an allylic halide. We will almost always go for the bromide because we can buy NBS really cheap. The chemistry works. You can't mess it up. You throw the things together. You shine a bright light on it with some peroxide. You come back in an hour and it's done. It's just that easy, okay? Now you might remember the mechanism. We briefly talked a little bit about this last semester, that NBS can be involved in free radical chemistry, and I told you we would talk about it at a later date, and here we are. So NBS, in the initiation step, if we shine a bright light on it, actually undergoes this bond homolysis, and you end up with what's called the succinimidal radical, the nitrogen-centered radical, and the bromine radical. And this bromine radical is quite important. It comes into the propagation step, extracts the allylic hydrogen. You get the allylic radical plus HBr. The allylic radical then reacts with the bromine that is generated from NBS, and you get the allylic bromide. The bromine radical then comes back in, and this continues on and on and on. Okay? So how do we get bromine from NBS? I think last semester I just told you that in water it decomposes slowly to generate bromine. There is a mechanism for it, and it looks something like this. It's a little weird in that the nitrogen, we believe, gets protonated by HBr. Where do we get the HBr? We get the HBr from here in the first step. So NBS reacts with the HBr. You form this protonated nitrogen that is very unstable. It's a very, very good leaving group. Why is this nitrogen being positively charged so unstable? If we draw the resonance structures for these carbonyls, what kind of partial charge would we put on the carbons? Partial positive charges, right? Because oxygen's electronegative, right? Would putting partial positive charges next to a formal positive charge be a stabilizing effect or destabilizing effect? Destabilizing, because we know that like charges, they don't attract one another, they repel, right? And so this is a very good leaving group. It doesn't like to be positively charged. And so what happens is, it's kind of cute, the bromide functions as a nucleophile on bromine. And this functions as a leaving group, and you get molecular bromine. And this happens pretty slowly. And so it keeps the concentration of bromine essentially zero, because once we generate a little bit of bromine, it's immediately consumed by the free radical. Okay? And so the free radical concentration has to remain close to zero, so that means that it reacts very, very quickly with any bromine that we generate. The cool thing about this reaction is succinimide is not terribly soluble in dichloromethane, and these reactions are typically run in dichloromethane. So as the reaction occurs, it falls out of solution as a white crystalline solid, and that makes the equilibrium lie to the right. All right, so we now know that we can generate allylic halides using free radical chemistry. We know that we can draw resonance structures of allylic radicals and allylic cations and allylic anions pretty easily. Hopefully the power is going to stay on here, right? And we know that an allylic system, you can think of that as 3 atomic p orbitals, right? But there's actually molecular orbitals. How many of you remember your molecular orbital theory from Gen Chem? A little bit, probably, right? I hope a little bit. In a allylic system, we have 3 p orbitals, 1 on each carbon. They are all of the same energy. Each one of these orbitals you can think of as having an electron in them, in an allylic radical. How do I take those 3 p orbitals and make molecular orbitals out of them? I add them together. And what do we mean by add them together? I have to account for all the electrons. That's true. Did I correctly draw those p orbitals? How do I correctly draw a p orbital? What am I missing? What's this? It's a node. So I'm missing something. How do I get a node? Close. There are signs associated with the lobes of the orbital. I have a plus and a minus. The computer software calls that red and blue. Okay? Like Democrats and Republicans. All right? So you have things that just don't get along very well, right? And if you have an equal number of positives and an equal number of negatives, they subtract to give a node. There is a node right through there. I've got an equal amount of positive on this side, an equal amount of negative on that side, and it cancels. This actually comes from wave mechanics. For those of you who've had physics, you probably talked about wave mechanics. In high school, if you took physics, you probably did a wave pool where you saw waves in the pool, and they could either constructively add or they can destructively subtract, right? They can do those things. So you have a wave coming in this way, a wave coming that way. You can either get a tidal wave or you can get just a little something on the beach, right? So you have constructive and you have destructive addition in wave mechanics. It's as much physics as I want to go into. But taking those 3p orbitals that look like that, I can combine them in different ways to get 3 new molecular orbitals. What does that tell me about orbitals? If I take 3p orbitals and I have to get 3 molecular orbitals, what does that tell me about orbitals? Okay, you're on the right track, just not using the right word. Close? They are conserved. What does that mean? I cannot create nor destroy them. I can only transform them, right? So if I come in with 3 atomic orbitals, I have to generate 3 molecular orbitals. Not 2, not 4, not 25, okay? There are only so many ways to do math, okay? And if you think about it, you get these 3 molecular orbitals. Psi 1, Psi 2, and Psi 3. Or molecular orbital 1, molecular orbital 2, molecular orbital 3. What can you tell me about those 3 molecular orbitals just by looking at them? They're equal? What do you mean by equal? Well, okay. But what does that give us? We do have an increasing number of nodes, right? We notice here at Psi 1 we have how many nodes? We have 0 nodes. The electrons can actually be delocalized over all 3 atoms in Psi 1. In Psi 2, how many nodes do I have? I have 1 node. In Psi 2, or Psi 3, excuse me, I have 2 nodes. Psi 1 has how many nodes? 0. Psi 2 has? Psi 3 has? So what's the equation to figure out how many nodes I have? Yeah. Each time we go up, we have to add a node, right? We have to add a node as we do this type of mathematics, okay? What do these nodes tell us? This is an allylic radical. What does this tell us? In Psi 1, how many electrons do I have? I have 2. What is that? It's an electron pair or a... Think about the allylic radical. What would that be? It's the pi bond. That's right. It's the pi bond. And notice the pi bond can either be between these two carbons or these two carbons, and that's delocalized over the whole system, right? Psi 2 has how many electrons in it? 1, and it's the free radical. And what does it tell us? If I look at that molecular orbital, what does it tell us?
It can be over in the left or the right.
It can be on the terminal carbons, but it can't be where? It can't be in the center because there's a node, right? This is the molecular orbital understanding of doing this. Which would you rather spend your time doing on paper? Thinking about drawing orbitals or pushing some arrows? I'd rather push some arrows. But the arrow pushing has reality in molecular orbitals. That's what I want you to understand. I am not on an exam going to give you a huge system and ask you to draw all the molecular orbitals. I will limit it to simple allylic systems, okay? But you need to understand that arrow pushing has its origin in molecular orbitals. It has reality. Molecular orbitals do exist. They are mathematical probabilities of finding an electron. You have to have supercomputers to actually figure out molecular orbitals on big structures. But it can be done. Okay, it's called quantum mechanics. Okay? So, what would be another name for that orbital? Huh? Oh, you could name it pi. This has a pair. What does this one have? It's a single electron, but it's an occupied molecular orbital. It's a SOMO, S-O-M-O. It's a singly occupied molecular orbital. Remember from general chemistry, you had HOMOs, highest occupied molecular orbitals, but those always had a pair of electrons in them. So if we had, instead of the allylic radical, we had the allylic anion, what would be different about this diagram? I'd have an electron here, and it would be spin paired, right? And it would be the highest occupied molecular orbital. What do we call the antibonding orbital here? LUMO, the lowest unoccupied molecular orbital. And these are going to be important terms for you all to know when we get into Diels-Alder reaction, because it turns out that the highest occupied molecular orbital of one species reacts with the lowest unoccupied molecular orbital of another, and it forms carbon-carbon bonds. And yes, we can push arrows, but it's not as satisfying as seeing it through the molecular orbitals in terms of a good explanation. So, if I gave you 3 p orbitals, one side blue, one side red, could you come up with those combinations? I want to see the heads go like this. Of course you could, right? Of course you can. How would you get psi 1? Line them what? That's really just lining them up like this, right? And I don't have them all drawn to scale. That's psi 1. How would you get psi 2?
Just to clarify, by psi 1, are you talking about, what are you referring to when you say psi?
When I say psi, I'm talking about the molecular orbitals.
Are you talking about the very bottom one?
I'm talking about all of them. Psi is a generic term for orbital. Psi 1 is the lowest energy. Psi 2 is the next up. Psi 3, you can go up to psi infinity, but not in this class. I dare you to go home tonight and cut them out of paper, make some molecular orbitals, and come up with those 3 molecular orbitals from those 3 atomic orbitals. You can do it. It's just wave mechanics. It's just a positive and a negative cancel, or a positive and a positive reinforce, where a negative and a negative reinforce. And what you'll find is there's only 3 combinations that work. Okay? Actually, if you want to, you can just get colored marshmallows. Put 2 of them together. It works really well. And then you can eat it afterwards. Okay? If you're working with your partner, don't eat the ones that they've touched. Flu's going around. Okay? We know that resonance results in energy stability. And that comes from molecular orbitals. The fact that these orbitals are spaced out over multiple atoms and the electrons can exist in those multiple atoms allows that to happen. That has the effect of lowering the energy of those molecular orbitals. Lowering the energy of the molecular orbitals lowers the energy of the system. Okay? And so we can think about the same thing in terms of cations, anions, radicals, right? Benzene rings, all of these things, because we can draw resonance structures, we know that the systems are going to be more stable. And as we get into the chapter about talking about aromatic rings, it turns out that they are so stable that they don't even behave like pi bonds anymore. They have special chemistry. Okay? We know that pi bonds, we can add things across them. Guess what? You can't add things across a benzene ring's pi bonds. Can't do it. Okay? And so we get such stability out of this resonance business that it works kind of some magic, if you will. Okay? So we've got about 9 minutes left. Let's do a little in-class exercise. A little throwback to chapter 12. I wanted to throw this in because your heads are probably hurting right now from orbitals. So let's stop thinking about orbitals for a second. Let's think about just some reactions. So I want you to assume standard workup where needed. And I want you to think about it at 2 levels. I want you to think about it in terms of the functional group transformation, and then I want you to think about it in terms of the specific compound that you get. So A plus B gives what? And then what specifically does it give? Okay? What kind of product are we going to get for A? We're going to get a Grignard. I know I'm going to get a Grignard because I have some type of halide reacting with magnesium. Specifically, what do we get? Yeah, we get phenyl magnesium chloride. That's A. But looking at it, I knew I had an aryl chloride, I had magnesium. I know I've got to get a Grignard. Okay? That has to roll off your head. Now, I can take that Grignard in the second reaction, and what am I going to get for B? What's the functional group transformation? I'm converting a Grignard into a what? Into an alcohol. Specifically, what kind of alcohol here? Secondary? Primary. And how do I know it's primary? There's only one carbon, right? There's only hydrogens on this carbon. There's no other carbons. So when I make the carbon-carbon bond from the Grignard, there's only going to be one carbon-carbon bond that's made. So I know I'm going to get a primary alcohol. How would I do the mechanism? Where would I start pushing arrows?
The bond between the carbon and the magnesium.
That's right. So we would start at this bond and we would draw a double-headed arrow to what? The carbon of the carbonyl, the formaldehyde, and we would break that weak pi bond, right?
I see how this is
Oh, you're following it now. Okay.
just figuring it out.
All right. How about the third reaction? What's the functional group transformation? What are we starting with? I'm starting with a ketone and I'm getting a what? And I'm getting a tertiary alcohol. How do we convert ketones into tertiary alcohols? What do we add to them? Grignards or alkyl lithiums. So what could C be? What's changing and what's staying the same? I'm adding an ethyl group. If I look at this, the aromatic ring doesn't change. This methyl group doesn't change. This carbon is changing from a carbonyl to an alcohol, carbon. But these two carbons right here have to come from somewhere, don't they? They're not in my starting material. So what are they? Well, diethyl ether would go here. It's the solvent. But where would I get the ethyl group?
From the Grignard.
Yeah, so I could use ethyl magnesium bromide. I could use ethyl magnesium chloride. I could use ethyl magnesium iodide. I could use ethyl lithium. Woo. I could use any of those things that I want. What are the products for the fourth reaction? Lithium bromide is going to be a salt byproduct. Yep, that's going to be D or E. And what's the other one going to be? Yeah, that's right. Yeah, it's lithium on a cyclopentane. It's cyclopentyl lithium. Yeah, exactly right. That's what we're going to generate, right? So you need to start knowing these reactions in terms of functional group transformation and then mechanism, okay?